Okie dokie, folkies. In this screencast, we're going to take a look at the product rule for derivatives. We have already seen the power rule for derivatives. It's very straightforward. We like it a lot. And so the question is, how do we deal with products? So the story should be told about Gottfried von Leibniz. He was one of the developers of the calculus. The story goes that at about 29 years old, he realized if we let f of x be x and g of x be x, then f prime of x is 1 and g prime of x is 1, but f times g, that's x squared, whose derivative is 2x, which is not the same as multiplying these derivatives together. And so the story goes, it was November 11, 1675, he realized that this was the case. And he locked himself in his room and only came out for food, that sort of a thing. And 10 days later, proved the product rule that we will talk about. His comment on that was, quoting now this is a really noteworthy theorem. So with that as the backdrop, here's the theorem. If I'm looking for the derivative of a product, u times v, then we take the derivative of u times v plus the derivative of v times u. That's an odd result. We take the derivative of the first times the second, the derivative of the second times the first, add them together. Why would that work? Well, let's take the limit as h approaches 0 of our function at x plus h minus our function at x over h. This leads you to ask, hey, why is there this big space in the middle? Well, for reasons that will only make sense because I know what's coming, I am going to add 0. And so much of math is adding 0 in a creative way. In this case, I'm going to subtract the quantity u of x plus h v of x, and then add it back in. U of x plus h v of x. So I haven't changed the value, but I have changed the appearance. Here's what that does for us. It allows me to split this thing down the middle and write two different fractions whose denominators are both h. The fraction on the left has these things in the numerator. The u of x plus h is a common factor. There's the rest of it. And over here, v of x is the common factor. So you might ask yourself, self, what happens to this thing as h approaches 0? Well, this thing as h approaches 0 becomes the derivative of v with respect to x. What happens to this as h approaches 0? That's just u. And then what happens to this as h approaches 0? Well, as h approaches 0, that is du dx. And this is unaffected by h going to 0. So I have u dv dx, just like here, and v du dx, just like here. So the way the product rule goes, the product rule is so much fun. It's 1 prime 2 plus 2 prime 1. Oh calculus, how tough are both your branches? If this is function 1 and this is function 2, it's 1 prime 2 plus 2 prime 1. The product rule, it's so much fun. So let's make sure that this thing works. Let's find y prime if y is the function 2x plus 3 times 3x squared minus 5. And you're thinking, that's a product. The product rule applies. And it does. The product rule is so much fun. It's 1 prime. So the derivative of 2x is 2. The derivative of 3 is 0. 1 prime. 2 plus 2 prime 1. Well, what's 2 prime? The derivative of x squared is 2x to the first. That gets multiplied by 3. And conveniently, the derivative of 5 is 0. And so we do a little bit of simplification here, and we get 12x squared plus 18x. That's this part, plus 6x squared minus 10. That's this part. And so that's 18x squared plus 18x minus 10. So how do we verify that this is in fact true? Well, you could expand the brackets and get that y is 6x cubed plus 9x squared minus 10x minus 15, whose derivative does indeed check out using the power rule. All right, one more way this could pop up. Let's let f of 4 be 10 and g of 4 be 5, and f prime of 4 is going to be negative 2, and g prime of 4 is going to be negative 1. I want to find the derivative of f times g at 4. And again, the product rule is so much fun. It's 1 prime, 2 plus 2 prime, 1. And that, just by substitution, we just plug everybody in, and bada bing, bada boom, and we've got it. So we have a product rule, we have a couple of ways that we like to use it, and we're all done. So there, that's it, all she wrote. Okay. Quotient rule comes up next, friends. Thanks, everybody.